you ever be able to travel through time? The answer is probably not. So thank you so much. It's great to be here. Thank you so much. Enjoy the rest of the conference. No, the answer is probably not, but how do we know this? We have a lot of ideas about how to travel through time, but in science, until an idea is supported by evidence, until we can come up with some kind of experiment or demonstration for it, it remains just that, a good idea. And most of our ideas are all, for how to travel through time, are all probably impossible. But there are two things wrong with what I just said. One is that word, probably. And the other is, it can probably be best formulated in a kind of complicated way, which is, why not? Why can't you travel through time? We're asking these questions, but before we get there, we should actually answer a much more fundamental question, which is, what is time? If I make a coffee date with a friend in Manhattan, I have to specify at the minimum 4 pieces of information to do so. I have to specify the east-west street, the north-south street, and then the floor that the cafe is on. Maybe it's on the 20th floor. But those 3 pieces of information aren't enough. I also need to specify what time the meeting is going to take place. So in this sense, time is a coordinate. It's a dimension. But at first glance, time definitely behaves totally differently than the other spatial dimensions, because it only seems to go in one direction. I can move backwards and forwards along Fifth Avenue, but I can't run backwards in time. And in this sense, it seems like time behaves totally differently than these other coordinates, these other dimensions, because space, my experience of space depends totally upon where I am, upon what I'm doing, about my point of view. For example, having coffee at a cafe in Manhattan is extremely different from, say, parachuting into the middle of a volcano. But with time, it seems like it just moves forward in one direction for all of us at the same rate. Space, I can probably manipulate, I can do things with, but time, I can't do anything about. So in this sense, time and space are totally separate things. And then came Einstein. Einstein pointed out that time and space are actually on the same footing, because he pointed out that my experience of time can actually change depending upon how fast I'm moving. And this might seem like a crazy thing, but this has been verified experimentally for over and over for a very long time. But you say to yourself, this is crazy. I've never experienced this. I've flown, for instance, from Budapest to New York and back, and when I got back, the clock on my grandma's wall matched up perfectly with my watch. There's no difference here. Well, this clearly is not true. It turns out that the effect is only really large when you're going at some sizable fraction of the speed of light, which is the top speed of anything. And so if you're going at almost near the speed of light, time can actually change for you in a measurable way. And this has been measured over and over in many ways over the years. Our experience of time can actually change in a measurable way depending upon how fast you're going, okay? But the interesting thing about it is that, so we've measured this over and over many times with experiments, and we've verified that this is actually a true thing, even though you may not experience it in exactly that same way. So time can actually can actually change depending upon your experience by how fast you're moving. And then things get even weirder when you add gravity. But what is gravity? Gravity is actually a bending of space-time. And that's important because the thing that Einstein pointed out, the fact that time can also depend upon your point of view, upon how fast you're moving, indicates that there's actually one. It's not fair to think of space and time as two different things. They're actually one thing, which is the fabric of space-time. And we know now that gravity is actually a bending of space-time. Gravity bends space. It's actually like a heavy bowling ball on a sheet of rubber. It bends space so that an observer that is thinks he's going in a straight line, will actually bend around a mass in space. For instance, a star. We know that a star exerts a gravitational pull on other things around it due to the force of gravity. but in this case, what's actually happening is space itself is being bent. We've verified this over and over experimentally over the years. And the crazy part is that if this is true, if gravity actually bends space itself, and since space-time is one continuum, gravity can also bend time. This also has been verified experimentally, as crazy as it sounds. We know that even an observer in space that gets closer to a large gravitational mass, like a star or something, bends around it. We also can verify that a clock that is closer to something that's exerting a huge gravitational pull will run slowly compared to a clock that is farther away. This is also verified experimentally right now in all of your phones. Your GPS system would not work with the accuracy that we need unless we were to correct by 38 microseconds every day, because the clocks that are in the GPS satellites experience time slightly differently than the ones that are down here. If we didn't do this correction, you wouldn't be able to rely upon the accuracy of your GPS. So imagine, trying to meet your date for a coffee in, say, Taormina, Italy, and instead relying upon your GPS, and you end up in the middle of Mount Etna. That's not such a good coffee. So gravity bends space, and gravity bends time. And if you take this to its logical conclusion, I'm a physicist, I like to take things to extremes and do insane things with it and go as far as we can possibly go. It leads to some crazy predictions. The extent to which I can bend space and space-time depends not just on how much stuff is in my star or whatever, it depends on how much stuff is packed into a very small volume. So the sun, for example, is pretty big, and there's a lot of stuff there, but it's also large, and so it bends space-time in a slight way. However, if I were to take all the stuff in the sun and pack it into, say, a coffee cup, the bending of space-time would be so great that it would be very difficult to, you basically couldn't avoid it. You would have to bend around it in a very crazy way. And if you put too much stuff into too small of a volume, you get a black hole. So what's a black hole? No one's volunteering, so I'll tell you. The black hole is a completely gravitationally collapsed object. It is the point at which you put so much stuff into such a small volume that the extent to which space-time is bent, it makes it so that the straight line that, for instance, a ray of light wants to go in bends so much that it actually can't make it out the other side. So if you just follow this picture that I was painting, right? Gravity bending space-time, black hole, so severe bending of space-time that the straight line of a light ray, of a photon, can't actually get out to the other side. This sucks, literally. It also sucks figuratively for an experimentalist, because if something in the sky doesn't actually emit anything, if it doesn't give anything off, it's very difficult for us to actually learn anything about it. We can't collect anything about it here on space. So the other way we could try to investigate black holes is to try to go to them. This is going to be difficult, because what would happen if you went inside of a black hole? First of all, you'd probably die. The gravitational forces would probably be so great that you would probably be ripped apart. But let's assume that doesn't happen. What would happen if you went into a black hole? We said that so much stuff packed into a small amount of space bends space-time, but what could such a severe bending of space-time actually mean? Imagine you're an ant that you didn't see before. Imagine you're an ant living on a piece of paper. To get from one end to the other side, you have to traverse the whole distance. Maybe it's pretty long for you. You're an ant, your legs are tired or something. But what if something, I don't know what it is, maybe gravity, what if something bent your space so severely, in such a way, space that were previously very far apart were now suddenly very close together, and you could just hop from one end to the other, as if they were right next to each other? Could a black hole actually be a bending of space to the point that there could be two different places that are separated by a regular distance that are actually getting close together that would be possible for us to traverse? And in an extreme case, could a black hole actually be such a severe bending of space-time that it would allow us to traverse between two moments in time as if they were happening in quick succession? I don't actually have the answer to that, but what if a black hole was actually a wormhole that would allow us to go between two different places in time? It's a great idea, so let's test it. I'm an experimentalist, let's test it. To test this idea, all we have to do is collapse a star and use negative energy for a sustained amount of time. I don't know how to do this. Okay, let's test it another way. We have other ideas. Let's test another. Let's find two cosmic strings. These are predicted things that will go the entire length of the universe, and they're huge, and we've never seen them before, but maybe they're out. Let's find some of them, and let's somehow go up to them and harness their energy to create a time machine. I want to do this too, but I have no idea how to do this. So it seems like all of our ideas as to how to test time travel, they require crazy postulates like this and things that are probably impossible for us to test. But is that it? Are we stuck? Are we basically completely screwed with respect to trying to test any of our ideas as to how to travel through time? Well, there are other directions we could go, because we have to do these crazy things. You have to collapse a star, you have to find cosmic strings or something like that. But we could also go in another direction. Are we basically stuck? Is there no way for us to try to understand the nature of time, to try to control anything about it, to even come up with a coherent description of what time travel would be? It seems like there's something very fundamental we're missing. We're dealing with huge energies, and we're dealing with very small things. And so is there any person you could ask about how to design an experiment where you use a large amount of energy put into something very small to understand the fundamental things about nature? Well, you could ask a particle physicist. Behind all of this discussion we're having is actually a fundamental puzzle that has been long-standing in physics, something that's still unanswered. How do we put together the world of the realm of the large, gravity, things that are like stars and planets, this thing we just discussed, and quantum mechanics? These two realms we understand separately really, really well. But when we try to put them together with our theory, with our math, we get nonsensical answers. Okay? And a place where and so this is something we've been trying to solve for a very long time, and a place in nature where the world of the large and the world of the small come crashing together is a black hole. If we were able to study this in a coherent way, we could understand more about the nature of space-time, and we would automatically learn about how to hopefully manipulate time. And so this is fun for me, because all the things we know about the fundamental nature of the world of physics are encoded into particles. And I'm a very lucky fellow because I am a particle physicist at CERN, at the Large Hadron Collider. And the LHC is the place where we collide particles together at the highest energies ever. It's a 27-kilometer tunnel on the border of France and Switzerland, buried 100 meters underground. And in this tunnel, we use superconducting magnets colder than outer space to accelerate protons to almost the speed of light. And we slam them into each other millions of times per second to collect the debris of these collisions to look for new, undiscovered fundamental particles. Its design and construction took decades of work by thousands of physicists from around the globe. And in 2015, we reached a milestone in human history, because we succeeded at colliding protons at 13 trillion electron volts, TeV. And it's the highest energy that we've ever used in a collider experiment. Higher energy is important because there is an inverse relationship between energy and time. Right now, the universe is about 14 billion years old, and it's huge. I hope that's a non-controversial statement. And when you have a lot of stuff, when you have a very large volume that is filled with stuff things are not very densely packed together, that on average means that you have a very low energy state. So the average energy of the universe right now is very low. It was not always this way. When we look in the sky, we see everything not just moving apart, but moving apart really quickly. So if we just run the clock backwards, run time backwards, not literally, but with our math, we run the clock backwards, we know that at some point everything had to be packed into one unfathomably dense, tiny, tiny, small volume from which everything at some point exploded and started to just expand into the vacuum. And this, of course, was the Big Bang. Higher energy is important for us because when we build a larger collider, we are actually briefly recreating the conditions of the universe a fraction of a second after the Big Bang. And for the Large Hadron Collider, we can get right to about this realm here. The most recent, and every time we do this in history, when we built a bigger collider, we have new things that we discover about nature. And the most recent discovery was this Higgs boson, which some of you have probably heard about in 2012, which was a fantastic discovery. It was made in 2012, led to a Nobel Prize for the guys that predicted it back in the 60s. And this is a fantastic achievement, but the Higgs boson does not teach us about the nature of gravity. It does not teach us about the nature of space-time. To get to that point, to get farther back in time where gravity and quantum mechanics have to have something to do with each other and where the nature of time will be revealed, we have to go even larger. We have to go back even farther. We have to get to something called the Planck Scale. And the Planck Scale is a place where gravity and quantum mechanics have to come together. They have to have something to do with each other. But to get to that realm, we need to go large. And the LHC, as big as it is, will never get us to that realm. So let's go bigger. The next generation of particle physics experiment is planned to be something like 100 kilometers around, and it will collide particles at 10 times the energies of the LHC. And this is great. This will be a fantastic scientific instrument. It'll teach us tons of stuff about the universe. It's way far away from the Planck scale. So let's go bigger. If we were to build a particle collider around the circumference of the moon, that would get us up to the tens of thousands of TeV range, which would be an amazing scientific achievement. Alas, still way far away from the Planck scale. No, I see the laughter already, so it looks on your faces. To get to the Planck scale, by some estimates, we would have to build a particle collider around the orbit of Neptune. And I see the looks on your faces. This sounds crazy, just as crazy as trying to collapse a star to create a wormhole with negative energy. But it's not, because we know how to build colliders. We do this all the time. It's just a matter of scale. So, I'm being a little bit glib when I say this, but the whole point is that we know how to do this sort of thing. We know how to go in this direction. And you might say to yourself, this seems crazy, James. In principle, we could do this. This is in principle possible. But is this just a nutty thing to say? Because isn't the LHC, a 27-kilometer tunnel, already a huge use of resources? Not even close, because considered in context. It cost about $8 billion to build the LHC, and it costs about $1 billion per year to operate it. The US Department of Energy contribution to that experiment is about $150 million a year, a fraction of its about $30 billion budget. And the US military budget is about $600 billion. And for some private sector examples, Uber is currently valued, if you believe this notion of valuation, valued about $68 billion. Palantir Technologies is valued at about $20 billion. And all of the privately held companies that are worth over about $1 billion each, they all add up to about $650 billion. If we as a society valued scientific curiosity, if we valued answering the fundamental open questions of nature, like what is the nature of space-time, as much as we valued more efficient, governmental surveillance of the citizenry, giving the state more efficient ways of oppressing immigrant populations or undermining strong service sector unions such as those covering taxis, we could definitely build in 50 years a collider around the circumference of the moon. And in a few hundred years, we could build a collider around the orbit of Neptune, and we could definitively explore the nature of space-time, of the Higgs boson, of multiverse theory, and understand everything there is to know about nature. It seems as though all of our ideas are practically impossible. So it seems as though this, I don't actually know if we'll ever be able to travel in time. If you came here for a yes or no answer, you got the wrong guy. Because I don't actually know this answer. What I do know is that time travel is too large of an issue for one person or one people group even to solve. Time travel is not going to be solved by a lone white male in his, using only his superior intellect. Much like the Higgs boson discovery or the discovery of gravitational waves, these things will only be possible to be addressed by having the collaboration of people from all around the world. It would not be possible for us at CERN to do our research if we didn't rely upon collaborators from all different perspectives, all around the globe, bringing healthy skepticisms and different points of view. Because in science, we actually want people to critique our ideas. We want them to say where they're wrong so that we can then make it better. We can make sure that it stands up and withstands scrutiny. So at CERN, for example, I rely upon this all the time. We would not be able to do what we do without this. the next generation of whatever it is we have to address in big science will also rely upon this. And so, a good scientist knows this. A good scientist knows that you have to have people around that you can rely upon to come from different perspectives, look at your idea, and tell you not where it's right, but where it's wrong. And a great scientist surrounds herself with people like this. And this is true of all great scientific leaders. And in fact, this is true of all great leaders in all fields. If you out there know of a leader who stifles criticism, surrounds himself with unthinking loyalists, attacks science, institutions of higher learning, and if this also person sows hatred or shows intolerance toward people from other cultures, religions, sexual orientations, and if this person also tries to stifle any kind of criticism from outside, from an open press, then this person is most likely a very bad leader, especially if they also start to invent things that don't exist, such as alternative facts, also known as lies. So at the end of the day, what should we do to address the issue of time travel? Should we go from the bottom up and try to understand, nature at its fundamental scales first, understand the nature of time by some kind of particle physics experiment? Or should we go from the top down and try to figure out how to collapse a star, which I think is awesome. I think that's a fantastic idea. But maybe I'm biased, but I vote for the particle collider. Once again, this question of time travel is whatever we end up doing to try to address it in a larger scale, in some kind of larger scale with the collaboration of nations. We still have to ask the very, very key question. How soon could this possibly happen? These are great ideas, and all science fiction is full of great ideas, but if they happen like 500 years from now, do we even really care? For me, it's okay because I feel like I have a duty as part of the continuum of science. It's okay if I happen to exist at one time when we were making steps forward, slower steps forward, that eventually humanity itself will make fantastic steps forwards because I'm just one piece of humanity, right? But how soon will this happen? How soon will all the people of the world decide to get together behind everyone and come together across borders and collaborate and really build something huge to completely understand the nature of time travel? It's only a matter of time. Thanks.
So that was incredible. I don't even know where to start. So Alexis.
I know where to start, yeah.
All
okay.
Right.
So James,
yes.
I've got a very simple question for you straight away.
Sure.
Because I'm an actor, and in acting you learn that there's always two sides to everything. And you said that gravity can bend time.
Yes,
no?
it can.
Okay. So surely it could work the other way around, that space-time can bend gravity.
Space-time can bend gravity. Actually, you're asking a very profound question because...
Oh, wow. We were looking for a stupid question.
No, it's actually a really good question. I actually encourage everybody in here to take some kind of maybe non-math-based course in general relativity. And
I run a lot of non-math-based courses.
You're making a joke, but it's actually awesome because it's really it's a mind-blowing experience. You don't have to actually understand the math really. If you do, that's even better. But you can really get a sense of it because it does it's a profound thing where what you're saying is actually true. It's the same thing. It doesn't matter actually if it's gravity that's bending space-time or if you have space-time that is doing some effect in the other direction. It's an equivalent description. I totally got out of your question, didn't I?
Yeah.
So if we have any audience questions, please queue up now. James, very quickly, do you believe in alternative universes? And if so, on those universes, are alternative facts actually truths?
Ooh, interesting.
Yeah, James, let's spin you around. I think we've got a better question.
3 short
here.
questions.
Sure.
Hi, James. First, I read 2 articles this year. It's one about the two-dimensional plane of time. It's Dr. Barr's theory. Is there anything wrong? Have you heard it?
No, I don't know this,
unfortunately. I think. Okay, the second one is the curvature propulsion time traveling when you really bend time-space in a curve.
Yes.
And then is that okay? What's wrong with it?
No, that's actually kind of what I was intimating here. I only had 20 plus minutes, and so I couldn't really go into it. But what you're saying is right. What we need to do is come up with this, we call it a closed time-like curve. And this, once again, you'll learn this in your general relativity course if you take it. That's the thing that's required for us to have some kind of time line that goes from where we are that could instead go, not just go in one direction in the future, but could in some sort be bent by such an extreme bending of space-time that it would come back and maybe end up before where you started, which would be crazy.
Thank you. And the third one, what book should we read?
There's a lot of popular level books. I can put up like a little like a reading list or something on Brainbar.
Good. Thank you.
So James, we had George Friedman this morning, who was basically talking about how war allows us to put innovation into things. And JFK famously said, "We're not doing it because it's easy. We're doing it because it's hard. Put a load of investment into space." I mean, what will it take? Will it take another war? What's it going to take from the general public to get behind the sorts of projects you're talking about?
I don't actually have a great answer for that. I think that what is going to need to happen is that people will have to get through this current bump that we have in this weird far-right sentiment, which always goes along with, this bizarre populism, which is some kind of really skepticism about science itself. When everyone that's saying this, who leaves a nasty racist comment on Reddit, they're using quantum mechanics technology when they're doing that. So we should not have this skepticism there. We'll have to get through this, push through this current. Don't hit it yet. We'll have to push through this current uptick in anti-science sentiment. I don't know if it's going to require a war as a shock to get us there, and I hope that's not true, but somehow we'll have to get through this to the point that we can get behind these big projects.
Our next question to your far right.
Hello, pleasure to be here. So I want to ask about quantum entanglement.
Oh, okay.
So the property that two particles can entangle each other, and if you change the state of one, then it immediately changes the other one. So
Indeed.
It's, in theory, faster than time.
Right.
And bear with me. What if we would put these two entangled particles near to a black hole? Would the time change in the phase changes? Or what would you guess?
Quantum entanglement next to a black hole. Well, there's maybe this is longer than 30 seconds that we have.
You can say yes or no.
Yes, totally. No. That is a fascinating concept, and it's a fascinating question. And these are the types of questions that, in lieu of answering it yes or no, these are the type of questions we need to be asking at the smaller scale to really interrogate what we don't understand about time. Because it's entirely possible that there are things that can, in principle, travel faster than time, but not necessarily things that you and I can do anything with. Like if we could figure out how to, number one, send information faster than time, then that's a great step forward. And we're still way, way far away from sending you, faster than time. But at some point we may get there. But these are the types of questions. The answer is I actually don't know what would happen if you put it in quantum entangled state here, put it through a black hole. I don't know.
Okay, thank you.
Yes.
We have some incredible volunteers at Brain Bar Budapest. I'm really surprised by that question. Very quickly, what if time travel has already happened?
That's a very profound question. And if it has already happened, then it's happened by, it has been realized by an advanced civilization that doesn't want to let us know that it exists. Because otherwise, why would we not know about it, right? This is the famous thing that Hawking came up with. He's like, time travel is probably impossible because we've never seen time travelers coming to visit us. Why would they skip us? Just because we're assholes?
Have we?
Yeah.
Hi, my question is, what do you think, what is the best movie about time traveling and stuff?
One of my
Great
favorites
question.
is actually the crazy Disney movie from the 80s called The Time Machine or something like that, or I forget what it's called, but it's this fantastic, super Baroque, weird, really bad science fiction movie where they're like a robot and some guy are running away from a flaming thing. That's my favorite time travel movie because I like the standard ones, like everybody has Back to the Future and things like this, because those are fun and they kind of do the kind of nerdy paradox stuff. It's like, what if I killed my grandfather? Oh no, multiple things. But I like it's actually called The Black Hole. Yeah, it's this Disney movie from the 80s. And this one's great because it's just wildly nuts, and I kind of like that one the best. I also like Interstellar, by the way, because that one, it had some really good, as you probably know, the models that they used, the visual models, were based upon real equations by Kip Thorne and his people. And it also, I wasn't going to tell you this, but I can tell you one of the secrets that the secret research that we do at CERN, we actually know I told you we didn't know so much about black holes. I was lying. We actually do know what happens inside of a black hole, and Interstellar is right. When you go inside of a black hole, you go back in time behind your daughter's bookshelf.
Yeah.
Thank you.
You heard it here first. Well done, sir. Very quickly, James, what do you think is more likely form of time travel? Hang out near a black star or travel at the speed of light away from Earth and come straight back?
We've got 2 questions, so
Whoa.
let's spin him
Okay.
around.
Hi, it's nice to be here. Let's put away all the facts
never
and
know.
imagine that some thousands of years passed and time traveling is possible. Can you think of any advantages of this, be it social or economical?
Yeah, the social and economic, I don't know about the economical advantages. Maybe if you could, I mean, probably what would happen is if you wanted an economical advantage of it, you'd be some kind of like hardcore dirty capitalist, and you're like, oh, I'm going to discover time travel, keep it for myself, go back in time and learn some key, like a market-based advantage thing and use that to my advantage to invest or something like that. Economic advantages, I'm not really sure. I know that, for instance, time travel would be really useful for, governments. They could use it for military purposes. Social versions, that's a longer question, right? Would you really, people say these things, oh, I'd love to go back and, be able to actually talk to Gandhi or talk to, somebody. It's like, that's interesting, and I would love to do that too. But, to what extent would I actually be affecting what happened back there? And this is kind of the sort of nerdy time continuum thing. But do I really want to affect what happened? In some senses, I would. I would like to go back and, punch Hitler in the face.
So perhaps your Uber or your pizza could arrive before you even ordered it.
Yes, there you go. Domino's is already, they're driving around with they bake it in the car when they get there, right? What if instead, right as you're about to hit order, it shows up already?
Shows up. Next question.
Right. Do you think humanity could even handle time travel? Like, who would we give it to? Imagine like Donald Trump having a time machine. It would be a huge problem. So
Huge.
Yeah.
tremendous problem.
I don't know how we would handle time travel. I think the way it would play out would be catastrophic. It's partially one of the reasons why, in a logical sense, the Hawking conjecture is probably right. Time travel is probably impossible for us because we've never seen anybody come back to try to do anything that we're aware of. I think that we actually, there's some conspiracy theories that happen. The conspiracy theorists online that will write things about CERN. It's like, oh, CERN is creating time skips, and because that's where this Mandela effect comes from. People remember things strangely, and they say, oh, this is why Donald Trump says things like, I remember a bunch of people in New Jersey cheering when the World Trade Centers went down because CERN is creating time skips or something. He's remembering it. Yeah, it was actually us. And I trust me. Trust me, if we at CERN could actually control time continuum and time skips, we would have chosen a very different current political situation.
Thank you.
So the Russians aren't hacking the election, CERN inadvertently did. James, that was an absolutely incredible presentation. Please join me in thanking James once more.